Hello everyone, in this video we're going to be talking about Fermat's little theorem. So previously in the book, we've been talking about Z mod mz. We introduced the integers modulo m, and we described it as a ring, meaning that the classes modulo m, the classes 0, 1, 2, etc. up to m minus 1, modulo m, that has an addition and a multiplication that satisfies several properties that make it into a commutative ring with 1. Now, so we're going to prove Fermat's little theorem. It's a property about the integer modulo p, but let's get there by discovering Fermat's little theorem, or how one would think about it and come up with Fermat's little theorem on your own. So something that is a natural question is the following. In fact, coming from an example of Fermat himself, something that is natural to think about is what are the congruence classes of powers of a single element modulo m. Take 2, what is the congruence of 2, 2 to the 2, 2 to the 3, 2 to the 4? What are those congruence classes? And one such example comes about because Fermat himself claimed that what we call the Fermat numbers, 2 to the 2 to the n plus 1, are primes, which was later disproved by Euler. But nonetheless, if we want to check if one of these is prime, so for example, let's say f37, is this prime? Well, let's ask two questions. One, is 3 a divisor of f37? And 2, is 5 a divisor of f37? Well, if it is prime, it better not be divisible by 3 or 5. It's definitely bigger than 3 and 5. So we can try to check if these numbers divisible by 3 or divisible by 5, and at least verify that that's not the case. This is equivalent to asking, is f37 congruent to 0 modulo 3, or is f37 congruent to 0 modulo 5? And those questions, if you think about it, we are asking, is 2 to the 2 to the n plus 1 congruent to 0 modulo p, modulo 3 or 5? Or equivalently, is 2 to the 2 to the n congruent to minus 1 modulo one of these primes? And the answer is no, but you can see already that the question requires knowing what happens with powers of 2 modulo primes, and is very much connected. Whether that is a prime is very much connected with the question of what are the possible values of powers of 2 modulo p. And for example, something like Mersenne primes also has to do with that question. So to answer this question, let's think about what happens with the powers of 2 modulo 3 and modulo 5. So we want to know what are the powers of 2 modulo 3 and modulo 5. Well, modulo 2, the powers of 2 are 2 to the 2, that is 4, which is 1 modulo 3. So 2 to the 3, that is 2 to the 2 times 2, that is 1 times 2. So this is 2. And then 2 to the 4 will be 2 times 2, 4, which is 1, etc. So we see that the powers are going to be 1 or 2 modulo 3. Okay. What about the powers of modulo? So this is modulo 3. What about modulo 5? Modulo 5 is a little bit more exciting, but not a lot more exciting. 2 to the 2, that is 4 mod 5. 2 to the 3 would be 4 times 2. 4 times 2, 8, which is 3. 2 to the 4, that is 3 times 2, that would be 6, which is 1. And therefore 2 to the 5 will be 1 times 2 is 2. And the pattern repeats. It will be 2, 4, 3, 1, 2, 4, 3, 1, etc. The key though here I'm going to get is that 2 to the 2 is 1 and 2 to the 4 is 1 in those two cases, and that's what's going to help me solve the question I had about Fermat numbers, because what is 2 to the 2 to the n? Well, 2 to the 2 to the n, that is 2 to the 2 times 2 to the n minus 1. So if n is bigger than, so if n is, for example, 37, n is bigger than 1, so I can do that. And so this is going to be 2 by the loss of exponents. This is 2 to the 2 to the 2 to the n minus 1, which is now by the loss of congruence. Well, this is just 4 to the 2 to the n minus 1. And 4 is 1 modulo 3. So by the laws of, by the properties of congruences, this is 1 to the 2 to the n minus 1, and powers of 1 are easy. This is just 1 modulo 3. But 1 is not minus 1, which is 2 mod 3. So no, 3 does not divide f of n, in fact, for any n bigger than 1. How about modulo 5? Modulo 5, I'm going to use this property. So I want a 4 out of it. So modulo 5, what I need is that 2 to the 2n, that is 2 to the 4 times 2 to the n minus 2. Okay, here I'm just assuming that n is at least 2. And here I was assuming that n is at least 1. So in this case now I have the 2 to the 4 to the 2 to the n minus 2. That is modulo 5. This is 1 to the 2 to the n minus 2. So this is just 1, which is not minus 1 mod 5, and therefore 5 cannot divide a Fermat number. Okay, notice that 2 to the 2 plus 1 is a Fermat number and is divisible by 5, and that is the case of n equals 1. So here it's key that we have n bigger or equal to 2. Okay, so this is for n bigger or equal to 2. This is for n bigger or equal to 1. Okay, so at least this example should show that we are interested in the powers of numbers modulo several, so modulo in a congruence class. Okay, so let's do a little bit more. So what happens, here's an example. I've done already a lot of computations. What happens when we do powers? Here we're doing powers modulo 15, and what I've done is compute all the powers of numbers, of all the possible classes, 0 through 14, and all the powers at least up to the 12th power. And there's a lot of data here. Of course, 0 is always 0, so that's boring. 1 is always 1, so that's boring. But then there is a bunch of things happening here. For example, 2, it goes into a cycle here, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8, 1. So there's a cycle in there. 3, 9, 12, 3, 9, 12, 6, 3, 9, 12, 6. There's another cycle there of it starts repeating. 4, 1, 4, 1, and so on. And you can see that every pattern will repeat. It is, of course, true that it will repeat because the powers of a number are going to be some numbers between 0 and 14. But as soon as there is a repetition, and it has to be a repetition because they cannot be, there's only finitely many choices. As soon as there is a repetition, we will see a cycle. So there's going to be always a cycle, and there's a lot of questions one can ask, like how long is the cycle? Here the cycle is of length 2. Here the cycle is of length 1. Here the cycle is of length 4. Are there other cycles of other lengths? Well, I don't know. Sometimes we do get a 1, and then it repeats after the 1. Sometimes we never get a 1. We get just tenths, say, for example, in that row. So what is happening? One way to get more clarity of what's happening here is distinguish between the units, like say 1 is a unit modulo 15, 2 is a unit modulo 15, in the things that are not units. Remember that units are those things that are they have multiplicative inverses that are invertible modulo 15. 2 and 15 are relatively prime, so 2 is invertible. And when it's invertible, we see that we actually get to a 1 at some point. 4 is invertible, we get to a 1. 5 is not invertible, and you see that we never get to a 1. There is a reason for that, and that's because 5 is not invertible, and we will see why that would be the case. So let's separate this table into two tables of units and non-units. So that's what I've done here. These are the units. So these are the units modulo 15, which we've otherwise called Z mod 15 Z cross. And these are in fact the not units, and they're in fact the zero divisors, what we've called zero divisors modulo 15. Sometimes you might see that as Z mod 15 with a 0. Okay, and so what is happening in these tables? Well, now we see a lot more going on. We see, for example, that there are columns like this column here of all ones, and that means that after that the pattern is going to repeat. So there is going to be, every cycle is going to finish here and is going to repeat. Some cycles are shorter, but at this column, you see we get all the units in this column again. So here are all the units, and all the units happen in here again. And the cycles restart there. So they all align here, and the cycles, all the cycles start there again. And we see that some cycles are length 1, length 4, length 2, length 4, length 4, length 2, and so on. With the non-units, we see that there's also cycles. So this is a cycle, and this is a cycle, but we never see ones. And there cannot be ones because of the property that is a zero divisor. But we also see that at some points, we do get a repetition where everything aligns again and everything starts over again. Okay, well, many things to think about, but what I want to think about really is about these kind of columns. Powers such that every power ends up being, for every number, x to the 4th power is 1. That is very useful, because when we saw in the case of Fermat's little theorem, we were looking for those cases when the power of 2, the first power of 2 that gives me a 1, was very useful in the computation. The same thing here, the first time that the power of 2 is 1 was very useful in the computation. So the fact that there is some power that works for all of the numbers modulo 15, that it works such that the 4th power of every unit is 1, that should be very useful in the applications. So let's explore that possibility. What is there such a power, and what is that power? What is this for? This is 15, this is 4, why 4? To make it more clear, the pattern, what we can do is 15 is composite. So let's look what happens in with prime numbers, modulo, prime modulus. So for example, what happens modulo 5 and modulo 7? Okay, so let's look at this data instead. Is there such a power? Are there such cycles? Again, we see that there is repetitions. There's a cycle of order 1. These are all 1s. This cycle is of length 4. This cycle is of length 4. This cycle is of length 2. And again, there is a 4th power such that every number to the 4th power, every unit, modulo 5, I'm not considering 0, which is all the powers are 0, but for every other class modulo 5, the 4th power gives me 1s. What happens modulo 7? Well, modulo 7, 1 is always 1, and there are cycles and so on. There are some long cycles. You see this, the cycle here until it starts repeating is of length 6. And it does happen that there is a power, in this case, an exponent of 6, such that every congruence class to the 6th power gives me 1. And so why 6? Why 4? I don't know. But Well, you can tell that this 4 is 5 minus 1, that this 6 is 7 minus 1. So one could conjecture that maybe that's the pattern, that every number, every congruence class, modulo p, modulo prime p, will be 1 once I raise it to the p minus 1th power. Another important feature is that if that is true, the next power, the numbers, you see in here, they were all scrambled, but here they appear again in order. After there is all ones, the next column would be all in order. 1, 2, 3, 4. What happens after the 6th power? In the 7th power, we see also 1, 2, 3, 4, 5, 6. They appear in order. Okay, so let's conjecture for now that if p is prime, then x to the p minus 1 is congruent to 1 modulo p for x not 0 modulo p. Or if you want, the property of the next column is that x to the p is congruent to x modulo p for all x, for all classes modulo p. This is in fact the statement of Fermat's little theorem, so it is true, but this is our conjecture. And again, just want to make sure that it matches what we just saw, that for p equals 7, that the 6th power gives me all ones. Here they are. And or for 5, so in the 4th power and the 6th power gives me all ones. And at the 5th power and the 7th power, that x to the 5th power or x to the 7th power gives me back x. And this is what happens here. X to the modulo 5 to the 5th power gives me x. And x to the 5th power gives me x. That 4 to the 7th power should give me back 4. So that seems to be true. Let's do one example just to be super duper sure. Let's do something larger. What is, let's work modulo 11. Does it work modulo 11? Let's see, what is 6 to the 10th power modulo 11? All right, let's try to figure that out. How I'm going to figure that out? Well, let's just start taking powers of 6. We have 6, then 6 squared, that is 36. And 36 is 33 plus 3, so this is 3 modulo 11. I'm just trying to get to 6 to the 10, so I actually don't have to do all the powers of 6. This is actually how one computes quickly higher powers, not all of them, but just take consecutive powers. So I'm going to do 6 to the 4 because I know 6 is squared. 6 to the 4 is 6 squared. This will be 3 squared, which will be 9 modulo 11. Okay. 9 is minus 2, so I'm going to use that in the next round. 6 to the 8, that would be 6 to the 4 squared. The 6 to the 4 is 9, and 9 is minus 2, and minus 2 squared is 4. So this is 4 modulo 11. How about then 6 to the 10? Now I can compute it by writing 10 in binary. 10 is 8 plus 2. So this is 8 plus 2. So it's 6 to the 8 times 6 to the 2. 6 to the 8 is 4 by our previous work, and 6 to the 2 is 3. 4 times 3 is 12, and 12 is 1 modulo 11. So the first part, this part works, that 6 to the 10 is 1 modulo 11, and 11 is prime. So it works there. How about, let's do one more. How about 6 to the 11? 6 to the 11 is 6 to the 10 plus 1, so it's 6 to the 10 times 6, so it's 1 times 6 is 6 modulo 11. So both parts of our conjecture work modulo 11. Okay, great. So it looks like we're almost there. Before I go on and actually try to prove the general theorem, I'm going to prove again that 6 to the 10 is 1 by using another different trick, which is going to be the method we're going to use in the proof of Fermat's little theorem. Okay, so I'm going to do again an alternative proof of is 6 to the 10 congruent to 1 modulo 11. And what we're going to do is the following. I'm first going to consider S1 is going to be not congruent, but just it's going to be a set of congruence classes, and it's congruent is going to be all the units modulo 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And S2, what I'm going to do is actually multiply everything by 6. Okay, I'm going to multiply every number by 6, and then what I get is 6. I get 12, 18, 24, 30, 36, 42, 48, 54, and 60. All right. Well, notice that 6, well, 6 is 6 modulo 11. 12 is 1 modulo 11. 18 is what's 18? 18 is 7. Modulo 11, 24 is 2. Modulo 11, 22, this is 8. 6 times 6, 36. 36 is 33 plus 3. 42 is 33 plus 9. 48 is 44 plus 4. 54 is 55 minus 1. So this is the 10. And 60 is 55 plus 5. Modulo 11. And now the key is to see that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 modulo 11. So this is another complete set of residues. So both S1 and S2 are complete residue systems modulo 11. And remember, that means that it's a set of 10 numbers that represent every class. Actually, a complete residue, I don't have the 0 here for the units. Okay, so it's for every unit, there is a number in this set that represents that unit modulo 11. And that is true both for S1, clearly, but also for S2. What that means then is, because I have all the classes, if I multiply all the numbers in S1 and I multiply all the numbers in S2, I should get the same thing. So 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10, it has to be the same as if I multiply 6 times 12 times 18 times 24 times 30 times 36 times 42 times 48 times 54 times 60 modulo 11, because they are the same classes, except that this, on the right hand side, I have a rearrangement of the classes modulo 11. Okay, but then they have to give me the same number. This, by the way, is 10 factorial, which is 11 minus 1 factorial. If you remember, this is 10 factorial. And by Wilson's theorem, this is actually minus 1 modulo 11. Okay, we're going to leave that aside, but it doesn't matter on this hand. Now, I'm actually going to factor the 6 out again of everything in here. This was 6 times 1, 6 times 2, 6 times 3 up to 6 times 10, and I can take a common factor of 6. This is 6 to the 10 times 1 times 2 times 3 times 4 times 10. But this is then 6 to the 10 times 10 factorial, whatever that 10 factorial was. It is again -1 by Wilson's theorem, but doesn't matter. It's 10 factorial. So what I got is that 10 factorial is congruent to 6 to the 10 times 10 factorial modulo 11. And in fact, 10 factorial is a product of units, so it is a unit, so it's invertible, so I can actually cancel it out on both sides. So either because you know Wilson's theorem or otherwise, I can cancel 10 factorial on both sides, okay? And what that gives me is that 1 is 6 to the 10 modulo 11, which is what I wanted to prove, okay? So in here, I've either used Wilson's theorem or that 10 factorial is a unit invertible. Okay, so I can actually multiply by its multiplicative inverse on both sides. But I got that 6 to the 10 is 1 modulo 11. And that is exactly what I wanted. So this proof should work actually for all primes. So we're going to do that. I'm going to first prove a lemma. The lemma is actually going to say that these two things are the same. Okay, so we're going to start with a lemma. Let P be a prime. And let A be an integer that is relatively prime to P. So it is not divisible by P. Then the set S A, which is A times 1, A times 2, A times 3 up to A times P minus 1, is a complete residue system for the units modulo P. So what do we have to show? I have to show you that every unit is represented, and also that every unit is represented, every every invertible class modulo P is represented here, and also that they are all different. Okay, so let's first I'm going to show that A times any one of these times I is not 0 modulo P for every I up to P minus 1. Okay, so that says that A times I is a unit. It's invertible modulo P. Okay, if A times I was 0 modulo P, that would say that P divides A times I, but P does not divide A. Then by Euclid's lemma, then P has to divide I. P divides I, which means that I is congruent to 0 modulo P, but that is not true because I is between 1 and P minus 1, so that leads to a contradiction. So therefore, this cannot be true. Okay, so we have proved that every A times I is something that is non-zero modulo P. Next, let's show that they are all different. Suppose A times I is congruent to A times J modulo P for some, so we're going to show that these are different for any 1 less or equal to I less than j less or equal to p minus 1. Those are all different congruence classes. Suppose for the contradiction that a times I is congruent to a times j modulo p. Then again, what that means is that p divides ai minus aj, which means that p divides a times I minus j. But again, p does not divide a, and again, by Euclid's lemma, then p has to divide the other factor, which means that p divides I minus j, which means that I and j are congruent modulo p. But if I and j are in the range p minus 1, those are all different numbers modulo p, and they are different in that range, then they have to be different. This implies that I is not j modulo p. So we've arrived to a contradiction that I is j and I is not j mod p, and this proves the lemma. This proves the lemma. Why is it already proved? Well, SA contains only units, by 1, and they are all different. Mod p, which means that, well, there are p minus 1 elements, so it means that the set SA has p minus 1 elements, which is the same as the number of units that are modulo p. So it has to be all the units. So SA, the first part says that SA is contained in the units. The second part says that there is as many units as there are units. So SA has to be all the classes, all the units, or it represents all the units. So we have them all. Okay. So that set is a complete set of is a complete set residue system for the units modulo p. And now we can state and prove Fermat's little theorem. Fermat's little theorem. It's called the little theorem, opposed to the last theorem. This is a very famous theorem of Fermat, but because it's a relatively minor result compared to the last theorem, we call this one little. And what it says is the following: let p be a prime and let a, some integer, be relatively prime to p, i.e. P does not divide a. Then a to the p minus 1 is congruent to 1 modulo p. Alternatively, you can say that for any b, for any integer, we have that b to the p is congruent to b modulo p. Okay, so how do we prove this? The proof goes as follows. Let's start with reducing everything to the case of relatively prime. So what happens if b is an integer, then either p divides b, in which case b is 0 mod p, in which case b to the p is just 0 to the p, which is 0, which is b modulo p, and it works, or p does not divide b, so b is invertible, it's a unit, and therefore b to the p is the same as, or b to the p congruent to b modulo p, is true if and only if b to the p minus 1 is congruent to 1 modulo p by dividing by b. So either b is 0 mod p, where it is true, or b is relatively prime to p, and we just have to show this part. Okay, so it suffices to show that if p does not divide a, then a to the p minus 1 is congruent to 1 modulo p. Okay, that's what we're going to do. How? We're going to use our previous trick. First, consider S1, which is 1, 2, 3, up to p minus 1. That's clearly a complete residue system for the units modulo p. And consider S2, which is a and 2a and 3a up to p minus 1a. By the lemma we just proved, both S1 and S2 are complete residue systems. Every unit modulo p is represented by one of these numbers. Both S1 and S2 are complete residue systems for the units mod p. But what that means then is that, so if I consider n, which is going to be the product of all the units, which is p minus 1 factorial, then n, which is 1 times 2 times 3 times p minus 1, that is congruent to, if I multiply all those numbers, but in a different order, which is a times 2a times 3a times p minus 1a, it has to be the same modulo p, because they are both the same set of numbers, but just in different orders. But the right-hand side, I can pull out multiples of p, or multiples of a times 1 times a times 2 times a times 3 times p minus 1 times a. So how many a's are there? This is a to the p minus 1. There is p minus 1 factor, so it's a to the p minus 1 times 2 times 3 times p minus 1. But now the right-hand side then is a to the p minus 1 times what I've called n modulo p. So I've arrived to the equation n is congruent to a to the p minus 1 times n modulo p. I have one step to do, which is that either 1 by Wilson's theorem tells me that n is actually minus 1 modulo p. So it is a unit, I can cancel it on both sides, or I can multiply by minus 1 in both sides, or 2, 1, 2, 3, p minus 1 are units. That implies that n is a unit, and if n is a unit, I can multiply n minus 1 mod p is a unit, and I can multiply both sides of my equation by n inverse. Okay, in both cases, I can do n inverse times n is congruent to a to the p minus 1 times n inverse, and that tells me these are going to cancel out, that 1 is congruent to a to the p minus 1 modulo p, which is precisely what I wanted to prove. So that's the end of the proof, and that's the proof of Fermat's little theorem. Okay, so now we have Fermat's little theorem. Okay. Let me do one example before we finish. I'm going to use Fermat's little theorem to prove something that is not about primes, okay? So show that a congruence where the modulus is not a prime. N to the 12 is congruent to 1 modulo 35 for all n that are relatively prime to 35. Okay, so if n is not divisible by 5 or 7, then n to the 12 is 1 modulo 35. How am I going to do this? By the Chinese remainder theorem, remember that n to the 12 is congruent to 1 modulo 35. This is what I called sometimes the mini Chinese remainder theorem, but it's just the Chinese remainder theorem for two congruences. This is true because 3 and 35 is 5 times 7 and 5 times 7 are relatively prime. This is true even only if n to the 12 is always 1 modulo 5 and n to the 12 is always 1 modulo 7. Okay, so let's check first that n to the 12 is congruent to 1 modulo 5 for numbers that the GCD of n and 5 is 1. So for units modulo 5, I'm hoping that that is true. By Fermat's little theorem, I know that for any of those, I have that n to the 4 is congruent to 1 modulo 5. Then, what is n to the 12? N to the 12 is n to the 4 to the 3. So this is 1 to the 3, which is 1 modulo 5. So it is true for that reason. And it boils down to Fermat's little theorem. What about, is n to the 12 congruent to 1 modulo 7 when the GCD of n and 7 is 1? So for numbers that are relatively prime to 7, yes, it is going to be true. Again, by Fermat's little theorem, we know that n to the 12, or Fermat's little theorem tells me that n to the 6 is 1 for units modulo 7. Okay, if a number is relatively prime to 35, it's relatively prime to 7. It's a unit modulo 7, so Fermat's little theorem applies in this form. And then n to the 12 will be n to the 6 to the 2. And by Fermat's little theorem, this is 1 squared, which is 1 modulo 7. So that is true. So these two conditions hold, so this condition holds. So by the Chinese remainder theorem implies that n to the 12 is congruent to 1 modulo 35 for all n relatively prime to 35, to 5 and 7. This is not true for numbers that are not relatively prime to 35. So if you take 5, 5 to the 12 will not be congruent to 1. It cannot be congruent to 1. Why is that? Is 5 to the n ever congruent to 1 modulo 35? This is something we began with, that zero divisors, could there be a power of a zero divisor that gives you 1? The answer is no, because if 5 to the n is 1, that would imply that 5 times 5 to the n minus 1 is 1 modulo 35, and therefore 5 would be a unit. Modulo 35, but the equation 5x is congruent to 1 modulo 35. The linear congruence has no solutions modulo 35 because the GCD of 5 and 35, which is 5, does not divide 1, 1 being this 1. Okay, and that's by our general theorem of linear congruences that those do not have a solution. Likewise, if A is a zero divisor modulo M, that implies that the GCD of A and M is something bigger than 1, and then A to the n congruent to 1 modulo M cannot have a solution because then it would say that A times A to the n minus 1 is 1 modulo M, but AX congruent to 1 modulo M has no solutions because the GCD of A and M is bigger than 1, which we would not divide this one. And therefore, a zero divisor cannot be a unit. A zero divisor cannot have a power that gives you 1. So that's why in the tables we saw at the beginning, you never have a zero divisor, some power of a zero divisor coming back to 1. Only the units come back to 1. And all the units go back to 1 by, for at least in the prime case, by Fermat's little theorem. In the next section, what we're going to see is what happens with something like this. What can we say in general about powers of a congruence class in the composite case? That's what Euler's theorem is about, and we will talk about that in the next section. Until then.